Washington State University. Go Cougs!
Welcome back to the course on statistical inference. We're in Module 2 talking about different classification methods for performing statistical inference. And in Part 3, we'll be looking at decision trees. So here's an example of a decision tree. And in this case, if we assume this is the data that we are trying to learn from, the data is represented by two features, the x and y acceleration, and we see the blue ones here, the 12 blue ones classified as activity play, and we have 4 classified as activity work. Now, the question is, can we learn a decision tree like this that would allow us to predict the correct class values for this data? So here is one possible decision tree that we could learn for this data. You see that basically it's asking questions about the different features and their values and then making a prediction at some point as we move down the tree. So first it is asking if the x acceleration is less than or greater than this t1 threshold. If it is greater than t1, we see that all of the examples that satisfy that constraint are activity play. So at that point, the decision tree would stop generating further deeper in the tree, and any other examples that fall down this path would then be classified as play. But on the left side of T1, we still have a mixture of work and play, so we are going to split them further. If we decide to split on T2 here, we see that 5 of the examples go down the left side, and the other 3 examples go down the right side. Now the 3 that are larger than T2 in this upper left quadrant here are all play, so pretty obviously we should predict play for those. But for the examples that go down into this lower left quadrant, we don't have all work. We have 4 work and 1 play, but we're still going to say that's good enough, and anything that goes into that quadrant is going to be classified as work. So our goal is to be able to construct these types of decision trees given this type of data. So let's look at the general algorithm for producing these decision trees and the methods involved, and then of course we'll look at how to do it in scikit-learn. Okay, so this is the main algorithm for generating a decision tree, and apologize, it's kind of a dense slide, but it's fairly straightforward. So we start off generating a root node, and for each of the nodes in our decision tree, we're going to associate a subset of the examples with it. So our root node is going to have all of the examples. So if we look back at our example here, the idea is that here's our root node, and it has all of the examples. I think we have 16 examples total, so all 16 are associated with this node. Then once we have this root node and its associated examples, we pass those into a procedure that's going to generate the tree for us. Now, generate tree, as you see, is a recursive algorithm, so it's going to just recursively descend deeper and deeper into the tree, splitting the data up until it gets to the point where it feels confident in a prediction, and then it will create a leaf node at that point. So any examples that flow to that leaf node would then be predicted accordingly. So to do that, we need to first check and see if the node that we're about to expand, if it's what's called a pure node, meaning that most of the examples have the same class. If it is a pure node, then we would, of course, assign it that majority class and would return and not expand any further. If it's not pure enough, then we're going to need to split the node. So to do that, we will first choose the best feature and best threshold on which to split. And how we choose that best feature and threshold we'll talk about in a second. But let's assume we have a method for making that choice. So then we divide up our examples based on all the examples for which that feature is less than or equal to threshold. We'll call that x prime. And therefore, the remainder of the examples in x minus x prime are going to be all the examples that have that feature value greater than the threshold. So for the node we're expanding, we create a left and a right child. The left child node gets our x prime examples. The right child node gets the remaining examples. And then we recursively generate the left and right subtrees by passing in the nodes and the examples associated with them. So this process continues deeper and deeper into the tree until essentially all of the nodes are pure enough and therefore turn into leaf nodes. So that's the overall algorithm for generating the tree, and highlighted in red here, of course, are the major questions that we need to ask, and therefore we need some sort of measure to determine what are the best features and thresholds and when is a node pure enough. Now there are several measures available that are used in decision trees, but the main one, and the one that's the default in the scikit-learn version, is called the Gini impurity measure. And this was developed by a statistician named Corrado Gini back in the early 1900s. And basically it's a way to determine whether the classes that are assigned to the examples in a particular set, that most of them are the same example. And the way this is done is we basically compute for all of the different classes in our problem. For a particular node, we compute the probability of each of those classes. And so that's just the number of examples that have that class divided by the total number of examples. And then we multiply those probabilities together for each pair of classes, except of course for the same class pairs. And so as you can see, if we have a pure node that has all of every example is of one class, then when we multiply that class against all of the other probabilities, all the other probabilities will be 0. So that means the impurity of that node will be 0, which is what we want. But if we have at least one other class, so there's at least 2 classes that have a non-zero number of examples, then at least one of these products will be non-zero. And so the sum over all of them will be non-zero. So that's one way to measure the purity of a node. And so nodes that have this Gini impurity near 0, we would consider pure. And it also provides a way for us to determine what the best splits are. So when we're about to choose a split, of course we need to figure out which feature to split on and then which threshold to try. Basically we try all possible features and all possible thresholds, and whichever one generates children that have the lowest impurity, then that's the feature and the threshold or the split that we'll pick. So the same measure is used in both cases. Now, having said that, there's still one issue that we need to deal with in decision trees, and that is whether or not, or how far do we split. Now you may notice back in our original tree here that this node here actually isn't perfectly pure. It basically has 4 work and 1 play. And so there's a question, should we split it further? So if we did that, we would wind up a situation like this, where we need to add one more constraint on the y acceleration feature as to whether it's above or below this T2 prime threshold. If it's below the threshold, then we have a completely pure node. All 4 examples are of class work. The Gini impurity is 0, and of course we would then predict work for any example that came down this path. And then for all the examples that are larger than T2 prime, that's just this one example. And so, yes, this node is pure, but that purity is only based on one example. And if this example were in any way incorrect, for example, it just wasn't clear whether it was play or work, we were having fun at work and we weren't sure how to classify it, or maybe we just classified it incorrectly. It should have been work, but we chose play for some reason. If that's the case, then making this split is not really motivated. We shouldn't do it. And that's called overfitting the data. We're trying too hard to carve up this space to get all pure nodes. And in the extreme, if we wanted to, we could keep generating this decision tree down to a very deep level and carve up this space into all 16 of our examples. But that clearly isn't what we want to do in statistical inference. So one way we can control how far to split is simply to limit how deep the tree can be. And so one of the parameters to the decision tree algorithm is the max depth, and we'll be using that to control how deep our tree gets. There are several other mechanisms available for addressing the overfit problem, and you can read about those in the documentation. We'll just use this max depth one for now. Okay, so let's take a look at the actual code. Again, you're probably getting pretty used to the general approach. We load in the particular module from scikit-learn, in this case the tree module. We set any parameters for the classifier that we need. In this case, we're going to be using the max depth parameter. We'll set that to 2, meaning that the trees can go to a depth of 2. Here we read in our data. Now we're only reading in 3 of the values, in this case the 3 acceleration values, and we could very easily read in all 9 of our values, but we're actually going to visualize this tree, and so it's a little easier to visualize if we just use a few features for now. So we read in the features, and again the class values for each of those, and so our data is in X and Y as usual. And like we've been seeing so far, we create an instance of the classifier. In this case, it's called the decision tree classifier. We set the max depth accordingly. We fit the classifier to the training data. We then use that classifier to predict the same data to see if it can at least get that right, compute the accuracy of those predictions, and then print out the accuracy. As I said, we're also going to visualize this. For decision trees, we're not going to be using matplotlib because we're not really plotting the results. We're actually wanting to visualize the tree itself. And it turns out that the tree module within scikit-learn has a method called export graphviz, which exports the decision tree in a special format that graphviz uses, and that's called the dot format. Now, in order to use to visualize this result, you're going to need to install graphviz on your machine. And if you go to graphviz.org, it's available for a variety of platforms, so you can install it. So to make the visualization look nice, we have to pass in the names of the features that are used. In this case, we're just using the 3. And we need to pass in the class names. So we're not just using numbers. And for a little added flair, our nodes will be rounded rectangles, and we'll fill them with a color that will tell us kind of how pure they are. Okay, so when we run this, this is the result we're going to see, but let's go ahead and run this in the actual code. So I'll get out of the notes. Again, here we are in a terminal in the source directory, and we're interested in the decision tree code. So let me run that. Okay, so we run the code and we get the accuracy value, 90, 94, 95% accurate, so pretty good. And also you'll notice that it created this tree.dot file, which again is the dot format used by GraphViz. So we want to visualize this, so the GraphViz package comes with a program called dot. It allows you to specify the type of output you want, and we'll output it as a PNG image. You pass in the dot format for what you want to visualize, and then you redirect that to the image file that you want to use. Let's even call it PNG. So that creates the PNG file down here, and when I open that up, we see our image of the actual tree. So you can see that it prints out a lot of nice information. So again, for each node, it prints out the feature value and the threshold that it chooses, the value of the Gini impurity, the number of examples that are in here. So initially we have our 56 examples, 26 are work, 30 are play. So this node is kind of on the play side, but as you can see, it's kind of a faded blue, not a strong prediction yet. So with the splits, we see that 24 of these 56 examples come down the left side, the other 32 down the right side. We're not quite to pure nodes yet, so even though they're a little bit purer, they're not completely pure yet, so we'll continue to split them. And the decision tree code in scikit-learn will continue to split until the nodes are perfectly pure. But of course, in our case, we've limited the depth to 2, and so at a depth of 2, it settles on leaf nodes. And again, some of them aren't perfectly pure, like these middle 2, but it still, of course, would predict the majority class for any other examples that would fall down these particular paths in the tree. So that's the result of our learning a decision tree for the data. And let me go back into the notes. One thing you may notice is that this accuracy for the decision tree actually turns out to be the exact same accuracy we got for the naive Bayes algorithm. But again, there are some other parameters that we could use to tune this. We could, of course, go deeper, choose a larger max depth, or we could also read in the other attributes, all 9 of them, the 9 features, that would give the decision tree a little bit more flexibility in the features that it chooses to split on at each node. So that's something you can try on your own if you want. So that's a decision tree classification method for doing statistical inference. And in the next part, we'll be looking at neural networks, yet another classification method for doing statistical inference.